Now let's try to understand multiplication. How to design circuits for multiplication. To understand that, first of all you should understand how you do multiplication using paper and pen. Okay, so let's try that. So example, let's say you have two numbers 1011, 1101. I am assuming that let's say these two are first unsigned numbers. After that I will extend this concept to signed numbers, right? Two's complementation. I mean, did you remember the two's complement representation? We will come to that point later. At this moment these two are unsigned numbers. If it is an unsigned number, what is the value of this binary number? It would be 240, 241, 2 square, 2 cube, 8 plus 2, 10, 10 plus 1, 11. This is 11 and this is 13, right? So 11 into 13, it would be 143. So we should get 143 as the answer for that, whether it is correct or not. I mean, we'll try this method. 1.1, 1. 1.1, 1. This is multiplication. 1.0, 0. Just usual multiplication. You know that, right? 1.1, 1. In that way, I am multiplying 1011 with the first bit of multiplier. So this is called multiplier. This is called multiplicand. You know that, right? Now this time I take second bit of multiplier and I multiply the multiplicand. Whenever it is 0, 0.10, 0.10, 0.00, 0.1, 0. In that way, second row will be created. These are all called partial sums, right? Now we will go to the third bit 1. With 1 we multiply 1011 again. Now we understood that we are going to get 1011, right? Now next time if I multiply with this one, we are going to get again 1011. This is a usual multiplication. Let us check whether it works for binary. Generally for decimal it works. So number systems are having very good reasonable logic. I mean, otherwise I can say all the base systems are compatible. That means if you can do multiplication using decimal, like using base 10, the same concept we can apply for binary, hexadecimal, everything. So that multiplication model works. So 1, 1, see 1 here, 1 plus 1 plus 1, 3, right? So if since it is 3, so 3 means what? 1, 1. That means this 1 is here and this 1 is carry. So 1 plus 1, 0. Then here 1. 1 plus 1, 0. Then here 1. 1 plus 1, 0. Then 1 will be carry. 1 plus anything, some 0 is 1 now. So this will be the answer, right? So if I simplify, I mean, if I convert it into decimal, what is going to happen? 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7. I would like to know the value. 128 plus here 8 plus 4 plus 2 plus 1. If I simplify, it would be 136, 140, 142, 143. Perfect. So using paper and pen, generally we solve problem like this, and that is exactly correct answer. That means it's working, right? So we try to implement this model, whatever I did. So exactly the same thing we are going to implement using circuits also. So I'm going to teach you three things. One is the basic model and very fast, which is array multiplier. Okay, but it takes lot of space. We will see that slowly. So first I start with array multiplier, which is directly taking this idea. Second one we will see sequential multiplier. So sequential multiplier. Then we see the optimized multiplier, which is Booth multiplier. Okay, so Booth multiplier is generally faster than this sequential multiplier. Okay, and it won't take much space like array multiplier. That details I will be clearly explaining, but I am just giving you the outline what I am going to teach you. Array multiplier, then I explain you sequential multiplier, then Booth multiplier. Okay, these three we will see. Sorry, so it is, this process is called array multiplication, this process is called sequential multiplication, and third one is Booth multiplication. All that we will see. So what I am going to do is I am going to do multiplication in a different way. So try to understand this way also. 1011 and 1101. So here you have partial products, right? So rather than adding them in the end, I will be adding whenever I create one partial product. That means I calculate the cumulative sum. We will see that 1, 1, 1. So 1, 1, 1, 1, 0, 0, 1, 1, 1. From now onwards, whenever a multiplier bit is 1, then multiplicand should be written. Next, so 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. Whenever this bit is 0, always you get, everything will be 0. Now immediately do the partial sum. You get 1, 1, 0, 1, 0. Then continue the process. Now third bit. So 1 again, since it is 1, we have to write 1, 0, 1, 1. But we know one thing, right? We have to start from where? From the third bit, right? 1, 2, 3. So here 1, 1, 0, 1. Again immediately do the partial sum. 1, 1, 1, 1 plus 1, 0, 1, 1. Then, so remember previous time we added here, next time we have to add here, okay, from here. So the bit is 1, then we have to start here 1, 1, 0, 1. So 1, 1, 1, 1, 1 plus 1, 0, then you get here 0, 1, 1 plus 1, 0, 1, 1 plus 1, 0, 1 here, right? So this would be the answer. 2 power 0, 2 power 1, 2 square, 2 cube. So this part if you see 15, this is 2 power 0, 1, 2, 3, 4, 5, 6, 7, 128. 128 plus 15 is 143. Already we have done here, right? So you can check it out. 000 followed by 4 ones. So what is the driving point here is, so this step if you understand, I am going to create a circuit which is exactly mimicking, otherwise which is going to simulate this model, okay? For that what I am going to do is, I will tell you. First of all, you tell me how to create 1011 which is multiplicand. Example, you have multiplicand, okay? So what is that? 1011. So now just I show you how to multiply using the circuits now. So far we have seen, we understood the idea, but now we are thinking about how to do this process using circuits, right? What kind of circuits are required here? I will tell you for that. Since the multiplier is 1, then we have to get answer 1011, correct? So you tell me what circuit can generate 1011 when I multiply with 1. Very simple. So actually 1.1 is 1, correct? This is nothing but result of this and this, AND gate of these two. Similarly, AND gate of these two, 1.0, 0, 1.1, 1. So I am showing how to create, this kind of result, just this part, okay? What you do is simply take your multiplicand. Let us say these values are M0, M1, M2, M3. Otherwise, let's use a name called A. A, not A1, A2, A3. This is your multiplicand A. I use M for multiplier. So this one, take one AND gate, connect one of the input to A3, remember it. Next, take another AND gate, slowly you will understand, don't worry. A2, take another AND gate, in that way take 4 AND gates, A1 and A0. Now here what you give is, you simply give 1, okay? That means this entire this input should be connected to one common variable. What is that? That is going to be a multiplier bit. So assume that that multiplier bit is M0. If I do it like this, then definitely we are going to get an output which is nothing but the first row, right? So always try to solve this problem using divide and conquer. That means whatever the subject it is, first understand smaller parts, then try to build a big thing. So always remember, every successful person will first of all will start with small things. After that he will make it big. Here also same thing. We are just understanding how to imitate the multiplication of one multiplicand versus 1 bit, correct? So let's try that whether it works or not. If M0 is 1, so what is going to happen? 1 will be passed to every AND gate. Now already A3 is having 1 here, 0 here, 1 here, 1 here. So 1.1, it creates 1 here, it creates C. So what is A1? 1. What is this one already? 1. 1.1? 1, right? So here you get 1. Then here it is 0.1, you get 0. Then here, this is 1 again, 1.1, 1. So what if I give M0 as 0? What is going to happen? So definitely 0.1, 0, 0.1, 0, everything should be 0. Yes, obviously one of the input of AND gate is 0, then we are going to get output as 0. So it's perfect. Now finally I understood how to create a circuit for one level of multiplication, otherwise one multiplication. right? We will be repeating this process. Then we will be repeating the circuit. That is what I am going to do. Now whatever the concept I am teaching you, that is actually array multiplier. Okay, so you understood this point, correct? But remember one thing, we need something extra. Are we simply doing, just multiplication? No, we are applying the multiplication with every digit. Then we are also adding two partial products, correct? So how to do that part we will see. Okay, at this moment I show this part, how to add one, partial product to another partial product. Example, this is partial product 1, this is partial product 2. How to add them? Okay, we will see. So how to first generate this partial product? Same thing, correct? How you generated this partial product? In the same way. For that you need another circuit. Let me construct here. Okay, so here again you require 1 2 3 4 gates, right? And remember one thing, all that, see, 0 0 0 0 is because of again your multiplicand and second bit, correct? So here A3 A2 A1 A0 are again fixed. A3 A2 A1 A0, remember it. Okay, I'll clearly show here. Second level we are doing, but remember one thing. So why I want to move my circuit to this side, I will tell you spatially. First blindly see the procedure what I am doing. A3 A2 A1 A0, there is another input. This input has to be, taken from where? Second input, because we are multiplying, otherwise we are getting this result because of second multiplier bit, right? So all the circuits to be connected to second multiplier, remember it. Okay, second multiplier. So here it is A0. So multiplier, for multiplier we'll give some names, right? This is M0, let's use M1. So now again A0 A1 A2 A3, here A0 A1 A2 A3, but the bit here is M1, here the bit is M0. Once you get these two results, what are we going to do? We are going to do addition. That means we need adder circuit. We have to add what and what? These two, right? We have to add these two. We have to add these two. That's it, right? For that, what to do? How to, neatly fix the full adder circuit? We will see. We need a full adder actually here. I will show that. Okay. Now see here. So I am taking again multiplication 1 0 1 1 versus 1 1 1 1. So I am showing only two partial sums. I mean two rows. One is 1 0 1 1. Second one also 1 0 1 1. So what are you going to do? Already I told you we have to add them, right? 1 plus here actually imagine one dummy 0. So unreal 0. 1 plus 0 1. Then we are adding these two, right? So 1 plus 1 0, you get here 1. 1 plus 1 0, you get here 1. 1 plus 1 0, you get here 1. Then you have to add these two, you get 0 here, sum, and carry should be propagated to the next level. That is what we need. Such a circuit I want. Now so I am showing with example circuit. We constructed this already, right? A0 A1 A2 A3. This is A0, this is A1, this is A2, this is A3. This is your M0, this is your M1. So here I am going to give input M0. Okay, example M0 here 1, I am going to give 1, depends on that. Okay, M0 is a variable. So don't worry how this M0, M1, M2 will be generated. Okay, that's a separate story. It's not very difficult to understand. Assume that let's say M0 contains a value, maybe 0 or 1, whatever, that will be propagated. So here we will be getting M0 dot A0. So exactly here, example, if it is 1 and this is really 1 0 1 1, then you are going to get here 1 0 1 1 because of the AND gate, right? AND gate's result I am writing here 1 0 1 1. Now what do you want to do again? Here M1 is 1. Then if this circuit is implemented, so A3 A2 A1 A0 again 1 0 1 1, then these AND gates are going to produce again 1 0 1 1. So what is the next step you want to do? You want to add them, right? So like this. That means these two AND gates you want to add, these two AND gates you want to add, these two and this one. I mean whatever the carry you get, with that you want to add this one, correct? So I want lot of adders here. Okay, we will see that. So definitely we need adders, we will do. Once you design, example, what I do is here I create one full adder. Otherwise I have one full adder here. Here I am going to construct full adder. Let's show with circle like this. Because why Mr. Example, this AND gate name is something X. My dear X, why do you want full adder? Because there is one more AND here, that's result and this result should be added, right? That's why here you require full adder. Similarly, this and result should be added, correct? So we require full adder. So why full adder, sir? Why not half adder? See here. Because sometimes what happens, so when you add these two, you are going to get sum, and carry will be propagated to the next level. In the next level there will be 3 digits. That's why I have to have full adder sometimes, right? That's why for simplicity I am assuming that everywhere I am fixing full adders. Okay, so here definitely you read full adder sometimes, correct? Why? Because this full adder has to add this and result and this and result plus this carry of this full adder, correct? That means this full adder is going to generate a carry, that also to be added, right? I am just explaining the requirement. So how to construct such circuit? It looks very big, right? Yes, definitely. Here also we need full adder. Assume that we have full adders here, that full adders are going to do the appropriate thing. Okay, so this full adder is going to add these two, this full adder is going to add these two, this full adder is going to add these two, plus of course carry, this full adder also adding these two and carry, in that way. Now after that what you are going to do, next level, right? M2. So we will be multiplying this 1 with 1011. What you get again? You get 1011. We will be adding 1011 from where? Recall. This is partial sum. Because of this full adders, see how many full adders you require? One here, one here, one here, right? And one here. 4 full adders. So 1, 2, see here. 1, 2, 3, 4, right? So what I want to tell you is that full adders, whatever the partial sum they create, here I can say some partial sum is created because of the circuitry, right? So that partial sum should be added to next again 1111. 1011, correct? So I show here. The next level when you multiply, you will be multiplying from here. The first time here, second time we start here, third time we start here. 1, 1, 0, 1. Okay. So now if you see, this 1011 is created by this AND gates. But the only thing is this 1011 should be added to this 00001. Okay. So this C is going to be 1. This full adder is going to create 0 sum. This full adder is going to create 0 sum. This full adder is going to create 0 sum. This full adder is going to create 0 sum, in that way. Okay, such a circuit we want. I am just giving the rough idea. So by this time you should have idea. Every time here also to add this sum and this sum, we need again full adders here. We will take the help of one more set of full adders. So here, how many full adders required, we will see that details later. Maybe sometimes I may not write exact full adders, but understand the concept. So why these full adders? Again to add here and here and here and here in that way, here, correct? So again you need some set of full adders. What I realized is in the every level, apart from the first level, in the every level you need AND gates to get the product. Second thing, you need full adder to add current row versus previous cumulative sum, right? So now finally I got a full realization that in my circuit which I am going to realize, I need full adders in every row almost and AND gates in every row. Let me create that as a package. I will show you example. So I am repeating the circuitry, correct or not? I will show that circuitry. So this AND gate and full adder one package, AND gate full adder, in that way the combinations are repeated, right? Are we having complete heterogeneous circuit? No, we are having completely repetitive circuit, otherwise same circuit everywhere, right? So see here, and that means you need some set of AND gates, and every AND should be associated with some full adder, right? So in that way, so we will be creating array multiplier. Now I will show exact implementation. So far you just got idea how that array multiplier looks like, what kind of components it will have, because it will be little bit difficult circuitry. That means it's a lengthy circuit and it has lot of gates and all. So directly if I take my array multiplier and if I explain, you don't understand anything. That's why I'm just giving you foundation what we are going to do. Okay, so in this process sometimes it will be boring, and sometimes what happens, so you will be thinking that we are doing what, but end of the day you will understand everything. So why I am doing all these things. Okay, now let me clear what I did finally. Just I explained you the multiplication process in a different way. What is that? Every time I am multiplying with one digit, then whatever the result I get, I am adding that result to the previous sum. That is what the way we are multiplying. The same concept I am implementing using the circuits. Now we will see the final circuit design, which is nothing but array multiplier. Okay, so you need everywhere one product, one addition, correct? That's why. So we will be having this kind of circuit first. First understand this circuit, and I will show the place of the circuit, what the circuit is going to do. First of all, this is your bit in your multiplicand. Okay, this is one of the bit in multiplicand, AJ. Now MI is a bit which is nothing but one of the multiplier bit, multiplier. Now this is carry in. So here you see, when you are adding, see, we will be adding first of all. Okay, so already I told you, when you add, then you get a carry, right? Example, when you add these two, if you get a carry, that carry should be propagated to next level, right? So similarly, so I mean here you see, for these two bits when you are adding, before that, so one carry will propagate to here, then that and these two bits we will be adding, right? In that way, everywhere, every line, so need one addition, but that addition is not only 2 bits, one carry also might come. Of course here there is no carry, but sometimes you get, isn't it? You should be prepared for that. So that is what we are going to do in this component. So I will be having one full adder because I am going to get one carry from the previous computation. So that is carry in. Now once you get full adder, before that, why this AND gate? Recall. So we will be multiplying, using one multiplier bit and one multiplicand bit, correct? Everywhere you see 1.1, 1.1. To do that we need AND gate, right? This AND gate. So what is this AND gate is now currently doing is mi.aj. So this is going to develop mi.aj once. So what is this blue line? Bit of incoming partial product. So once you generate this kind of, here I show this kind of bit using AND gate. So what are you going to do? We are going to add one more bit which is going to come from previous level of partial sum. So one bit is going to come from the next incoming from the previous level. So that I will be taking. I will show how to take it. Okay. So now this one, and example, this one is this one. Now what is this one? Just now I got this product, right? This one, because of this AND gate. Now we have to add. Sir, only these two? No. One carry comes from here, right? Previous level. So that is carry in. That's why this carry in bit, this AND gate result, that means the output of this AND gate, and one bit will come from the next level. So that all these 3 bits I add. When I do addition, then I will get sum, right? So thus sum is going to be the, again partial sum bit. So this sum is going to next level, right? If you have another addition, example here you see, this partial sum bit is added to this, right? Then you are generating one more partial sum bit. So this will be added to the next level, right? So that is what going to happen. So that is about this, sum. Next, anything else? So we understood what is carry in, we understood multiplier bit, multiplicand bit, they will be ANDed. After that, one incoming bit will come, and this one we have to add. Then you get sum and carry. Sir, what about the carry of this? You did not teach. Yes. So this full adder is going to get going to have a carry. That carry we will be sending to the next level. Okay. So here we will be having this kind of circuit here. That is going to generate a carry to the next level. Okay. So there will be one more this kind of circuit here also. Multiple circuits we will be creating. So these circuits carry we will be giving as a carry into the next circuit. That's it. Like we got a carry in from right side, right? In the same way, this carry is going to right side. That's it. So all these things I explained. Now I will try to connect this circuit to this problem. Okay. So let me show that. Example here, 1011 1111. You know the calculations. It is A0, A1, A2, A3, M0, M1, M2, M3. So first of all, let's have some calculation. 1 1 0 1, and after that 1 1 1 0. You know that, right? So you get 1 0 1 1 2 times because everything is 1. Now after that you do partial sum. So here I am not showing you. So how the circuit is going to do all this stuff first. So first what I do is I just allow partial sums first. 1 1 plus 1 0, 1 plus 1 0. I am not explaining the any computation here. don't try to understand. So finally, let's say this calculation is done by your circuit. Now what are you going to do next step? You tell me. Already you applied m0 into this one, or done, m1 into this one, done. After that partial product you got. Once you get partial product, then we will be doing what again? We are going to take the third bit. Now this moment I will be taking m2, which is 1. Then m2 will be multiplied with each and every digit of your multiplicand, right? Then what are you going to get here? First 1.11, then 1.11, then 0 1. Okay, this part also I don't want to explain now. So I would like to focus on the area where I can show the relevance of this one. Slowly you will understand. Example here. Okay, so here I show. First thing, what are the things you are doing here? I will show. So this is incoming bit, right, which is coming from the previous partial product. Okay, remember it. Apart from that, how did you get this bit? This bit you got because of m2 dot. So I can say that this bit is nothing but m2 dot a3, right? Remember. So 1 is nothing but m2 dot a3. Once you get it, then what are you going to do? Just we are adding these two. To add, so you need carry also, right? This carry is going to come, right? So this carry, whatever the, because of these two sum you are going to get carry, that carry, this bit we are adding, right? Assume that that bit is something x. Then we will be adding x plus m2 dot a3 plus this carry in, right? Carry in. Now see the circuit here also, carry in plus this is mi dot aj like m2 dot a3 plus some bit of incoming partial product. This is bit of incoming partial product. These three will be added. So once you do that, you will be getting again sum and carry. Carry will go to right side, okay, or left side, whatever, this side. Then sum will come down side. So that in the next level there will be another this kind of circuit. For that I am going to connect. Okay. So now this kind of circuit we will be repeating and we will be realizing, otherwise we are implementing multiplier circuit. We are going to do this, all this stuff using this. Okay, so clearly see what are the things we have. One AND gate, one full adder, right? So remember that things. So now I am going to construct complete multiplier circuit using these building blocks. Okay, this building block is important, focus on that, right?